Yeah, so suppose the data looks like this. So we have the variable y and the variable x, maybe just the x. Okay, so and the y maybe okay continuous variable. Yep. Now everyone is. Okay, so y and x, and y we have some continuous variables such as the okay, so like this. And the x is a factor variable. Suppose ABC, ABC. Then suppose we fit y on x, so lm y on x. Okay, maybe at first we may have to make it as a factor. So if x is a character, maybe we define x as factor x. Then x is a factor variable. Then typically the result is estimate, maybe estimate, and the standard deviation and t value and the p value. And we have intercept and the x factor b, x factor c. If intercept is negative 1.5, or maybe intercept is supposed to 1.65 and the xb is 0.4, maybe 5, and the x dot c is 0. Maybe 1.5, suppose. Then suppose we have some standard deviation such as this is the 0.2 and this is 0.3 and this is the 0. Oh, I think that these are should be the same, but anyway, okay, so suppose that these are all the 0.2, suppose. Then p-value, t value, the 2.5, and suppose the p-value is the 0.0, maybe 0.12 or something like that. Then what does this mean? So what does these numbers mean? So 0.5 is the difference between the level A and level B. So basically this 0.5 means that the level for factor B. So factor B, for factor B, I mean if x is equal to b, if x is equal to b, then y is 0.5 higher than that. 0.5 higher than x is equal to a. And the difference between x is equal to a and x is equal to b is significant. So for linear terms, for continuous variables x, it's clear. So if we fit y on x, these are the intercept and the slope. So the estimate is just a slope. But for factor variable, we have the baseline, and the baseline is actually in default the first one in alphabetical order. So here the a is the baseline. If you wanna change the level, the order of the factors, then you can specify the level option. So I think that within this, as factor, you can specify the level is equal to, I think like the CAB, then C becomes the baseline. But in default, the A is the baseline, and this 0.5 means the difference between the x is equal to b and x is equal to a. So sometimes suppose that we have group A, B, C, and just the group A is much smaller than other groups. The A is here, B is here, and the C is here, and there may be possibly the more category like D. And if A is the baseline and just A is lower than other groups, then always all factors are significant. So difference between A and B is significant, difference between A and C is significant, and difference between A and D is also significant. But that means only A has a different level. So we have to be careful about the significance. So sometimes if we see all variables significant, but possibly just the B, C, D are not different each other, but just A is different. So my recommendation is to make the largest group as baseline. I think that one of your project uses some demographic of the counties or cities or something like that. Then some variables explain the racial decomposition. So I don't know several groups, but I think that white and black and Hispanic, the Asian, and the more than 2 races, and maybe, I don't know, maybe 5 races. In such a case, in usual data set in the United States, the white is the largest group. So probably the white as a baseline is easiest to interpret. Okay, so if we make, for example, the Asian as the baseline, so that is a little more difficult to interpret. Okay, so the small group as baseline. Maybe if specific, it's still fine. But for example, if we have white, black, Hispanic, Asian, and others, okay, if others is the baseline, it's really hard to interpret the coefficient for example, white. So for example, the white people has so in some response variable, maybe 2.5 point higher than the baseline. If baseline is others, it's not clear what it means. So usually it's good to have the biggest group as baseline. Okay, that's it. And for final project, I think that all of your plan is reasonable, but the one thing that we have to be careful is to interpret data in a meaningful way. For example, we fit income on some other variables. Income on, for example, the state of residence, and the income on the educational level, and income on maybe the height of the person, and so on. But if the predictor includes the wage of that person, then of course wage is the majority of the income for most cases. So if we put that variable, sometimes the question becomes trivial. So we have to be careful about what variables to include to the data set, especially to the set of predictors. Yeah, that's it. Do you have any concerns on your final projects? So if you have some questions, you can visit my office hours, or the small questions can be asked by email. Okay, so today, at first, I would like to continue chapter 8 lab session. So last time that we did the regression tree and the random forest and the bugging. So this time that we do boosting. Yeah, boosting. So okay. So we start our session. sure. Oh, I see. Okay, so that we do boosting. So boosting is the fitting slowly. The idea of boosting is fitting slowly. So we calculate the fitted value, but we reflect only part of it. For example, that we estimate the weight by gender. And the overall, for overall population, suppose the average weight is 140 pounds, for example. Then we observe the weight by gender. And for male, that was 170, and female, 110. Then, but if you believe that that exaggerates the difference between male and female, just by chance, the male weight is too high. The majority of the observations is too high, and for female, it's too low. So the difference becomes very large, but we only reflect a part of it. Okay, male may be higher weight than a female, but suppose only we reflect the 1/3 of that. So then even if the sample mean is 170 for male, that we only adjust 1/3 of the difference between 140 and 170. So we estimate the male's weight as 150 and the female's weight as 130 rather than 110. So that is the idea of boosting. And we further regress the residual. So residual for male is 20, right? On average. So yeah, so the next, our start line is the male weight is on average 150 and the female 130. So the difference between each observation and 150 for male is fitted on some model again, fitted on the regression model again, and we reflect the difference. So every time we resample observations by bootstrapping, then we reflect just the partial information each time. So in that way, our decision boundary becomes the smoother. Especially the tree-based method, usually the decision boundary is not smooth. So just we separate the entire predictor space into two pieces, and we separate the level. So the decision boundary is not smooth. This decision function, I mean the estimated function, so fitted values are not smooth in the predictor space. But if we use the boosting, then it becomes the smoother. And also it's similar to the rich regression or lasso. So it shrinks to the coefficient shrinks to 0, shrinks towards 0. So that we only reflect partial information. So we avoid the overfitting if we choose the appropriate parameters. Okay, so that is the boosting. So that we would like to discuss that one. And we use the GBM library. So GBM library for GBM function. So GBM function is what GBM stands for. So it can be used for the boosting. Help GBM. So GBM, the generalized, the boosted regression modeling. So that's why we say the GBM. So the GBM. And we use the data in the MASS library, MASS library. So this data set has many data set. This library has many data set, and we use the Boston data set. Boston data set is probably the one of the most popular data sets. If you search on the website, often this is an example. The data set is in the sample code. And this is basically the data set for real estate, the housing price. by the town in the Boston metropolitan area. I don't know the zip code or the township, or I'm not exactly sure about the sample unit, but at least the sum of the city. So probably the town, I think the town. We have the 506 towns in the Boston metropolitan area, and each observation have these variables. And basically the response variable is the last one, the median, the house value. And this is actually in the $1,000s. And it's surprising that in Boston, the median house price is 24,000. But this is the data from 1970s. So that's why the values are so small. 19, yeah. And some other variables are predictors. All other variables are predictors. And this is the crime rate. And this is the some zoning. This is the INDUS, industrial something. So we have the several variables. You can see the definition of the variables. So if you type help Boston, you can see the crime per capita crime rate and the proportion of residential land that's zoned for the lots over the 25,000 square feet. It's pretty large. And proportion of non-retail business acres per town. And this is the CHAS is the Charles River dummy variable if the tract bounds river, 0 otherwise. And probably around the Charles River, then housing price is higher. For some people, it's strange that in US cities, the waterfront properties are higher than other places, even though we have higher chance of flooding. And NOx, some environmental variable. Nitrogen oxides the concentration and the average number of rooms and age of the house and the distance to the Boston employment centers and the radial index of accessibility to radial highways and tax rate, and the student-teacher ratio by town and the proportion of blacks by town. It's pretty complicated formula. And L-stat, the lower status of the population and something. Okay, so basically we want to fit the median value by other variables, such as if age is more than 20 years old, then the house price is cheaper and so on. Okay, so to get the same result for all computers that we set seed and the training, we have 506 observations. So we take the half of that observations to as a training data set, 253 index for training data and the test set. So test is the rest of the index. So TRN 1 to 506 minus the training data set. So TRN, yeah, so it's sorted and head TST, then the other half. Then boosting Boston. So we just use the BGM, so the GBM function, the median value on other variables, and data set is Boston, and only the training set. Oh, sorry. We have to specify several other things. So just distribution. Gaussian. So this means the just the error function. So error function. So linear regression use the least square method. That is the maximum likelihood method for Gaussian distribution. So for continuous variable that we have to say the Gaussian, we have to specify distribution is Gaussian. Then it will do usual linear regression for the continuous response. So if the classification problem that this should be the Bernoulli, the BERNOULLI, yeah, so distribution, then yeah, then that we have to specify the number of trees. So how many times do we repeat? And the interaction depth is the size of each tree, size of each tree. So we have the 5,000 that we just slowly reflect the each of the 5,000 trees, and each tree has the up to 4 cases. Then we do this. So 4 nodes. So the 4 is D. So the interaction depth is 4, and the number of tree, that is B, is equal to 5,000. And that is the boosting. I think we have to specify lambda. So, but the lambda isn't here. So that should be in the should have some default value. So the lambda number of tree interaction shrinkage 0.1. Yeah, lambda, I'm not exactly sure about the lambda value. So we have the 3 parameters, the D, B, and lambda. So we have to specify lambda. Yeah. Yeah, not exactly sure. So finally, that we have to specify lambda, and I think the shrinkage parameter specifies it. So yeah. So default is 0.1. So the 0.1. So this is pretty large when we consider that the B is equal to 5,000. But the 0.1 is the lambda. Then we get, yeah.
Can we use cross validation for determining lambda?
Yeah, cross validation. Yes, that we should do that. Yeah. So just that we are doing the default value. So basically, the lambda and the B are 2 related parameters. So basically, we only have to optimize one of those. So that we can change B, then do cross validation. Then we can see what's the best B. So lambda 0.1 may be too large, but usually we make lambda small, 0.01 or 0.001. Then we optimize B. That is sufficient. So yeah, so changing lambda, doesn't affect the result much if it's not too large. So if the lambda is 0.001 rather than 0.01, then just probably we need the 10 times more iteration. But if we do that, then that should be sufficient. So the lambda, we can make it small. So default is 0.1. Maybe the smaller lambda is better, but the lambda can be specified by this shrinkage option. Okay, then, okay, so we don't discuss this in detail, but in this way that we can fit this model. Then plot. And this is really hard to express. So if we fit just usual regression tree, we have tree to represent the result. But here we have iterated algorithm of tree, so we cannot use the tree itself to describe the result. And also we have many variables, so we cannot describe surface. So only way to describe the result is the y against each of the predictor. So that can be done by the plot and the model, and the I is equal to some variable, predictor variable. So then that we can see that this is the one predictor LSAT. LSAT is what? I forgot, but the some predictor. And this is the Y, so the median house price. So the relationship between LSAT and Y is here. So at first here, the function is flat. And after that, we have the steep curve. Then after that, it becomes less steeper. Then after maybe 22 or 3, it's almost flat. So this is the estimated the surface. We can do this for other variables. So for example, crime rate. Then we can describe in this way. So crime rate, actually after 20, almost flat. So just estimated the house price is here, but the here the crime rate is high around here. Then the crime rate, yeah. So actually property price is higher, and crime rate is lower than here. But of course, if crime rate is too high, then property price is lower. So probably in downtown, for example, the crime rate is higher. So that means the little higher crime rate has higher housing price. But in the suburb, it's certainly higher than this range, but the slightly house price is lower. Yeah, think about the Detroit. Crime rate is high and property price is low. And for example, around Wayne State, actually the crime rate is high, basically because we don't have many residents on campus. Many people during daytime, but not many residents. So the per population basis, the more crime. But certainly the property price is higher around Wayne State, near the Wayne State. So you can see the slightly higher crime rate has higher the property price that is possible for downtown. And so on. Okay, so then we have estimated it. And now that we want to extract fitted value of this model. So still that we can use the predict function. Predict function can be used in many algorithms. And this time that we want to predict the median house price for test set. So we specify a new data set. And it seems we have an option to change the number of trees. So probably we cannot choose the more than 5,000, but we can cut off in the middle. Then we can calculate the error size, the test RMSE, that is the square root of mean of fitted value. Maybe we should say the original value. Original value is Boston dataset and the MEDB. And we only use test set. And the difference between fitted and this, and the take square, and the take average, and take square root. Then 3.7, yeah, 3.79. So for Boston data, so okay, so the root mean square error. So typically this model has error of $3.7 thousand, $3.79 thousand, $3,790 as an error. And for this data set, if model is not good, the root mean square error is around 4.5. Model is really good, then 3.0 or something. So the 3.79 is not excellent, but somewhat reasonable. So at least better than linear regression. Probably if you do linear regression and do stepwise selection, you will get around the 4 point something. The sub 3 is very good. I think the one student did the 2.7 or 8. So that is really good. Yeah, so this is the boosting. So we don't discuss in detail. So actually we have to optimize the number of trees and yeah, also number of trees, and possibly we have to optimize the interaction depths. Usually just small number is fine. So 1 or 2 is fine. So yeah. So this is how we can do boosting. Yeah, boosting the random forest, these are usually better than regression or classification trees. Okay, so do you have any questions?
This might be out of the realm of this class, but could you, if easy or possible, whatever, explain the difference between boosting and descent? Like, how different is this boosting to doing the stochastic or stochastic gradient descent? I forget how you say that word.
Sorry, I'm not sure. The stochastic gradient descent is rather the algorithm, right? So algorithm to optimize some model. So
really what I was getting at is both of them are just doing very small steps to try and find where you're not getting any you're not getting any better results from taking another step, right? Is kind of the baseline idea
right.
of both boosting and gradient descent.
Oh, I see.
That's what I'm confused about.
Boosting is still the global, right? So the boosting basically fit the everything at once, but we only reflect the part of it. The gradient descent is, I believe, we only focus on some specific derivatives, right?
Okay, that makes sense.
Not. Yeah,
like it's a different viewpoint almost.
Yeah.
Okay, cool. Thank you.
But yeah. But in my image, just the stochastic gradient descent is really focused on more like the algorithm to get the optimization, right? So how to optimize it, right? So the boosting, we don't have any optimization problem. So just we don't have the sequence of optimization procedure. So boosting just optimize everything every time, but we only reflect the part of the result to the fitted value. Yep. Okay. So now we do chapter 9. And I think that realistically that we can only finish up to chapter 9. And chapter 10, probably that we can discuss some ideas briefly. So chapter 9, that we discuss the concepts and today, and the next time maybe we do some implementation. So support vector machines is still the supervised learning. So we have X and Y and how to fit Y by X. And the support vector machine, usually this is, when we say support vector machine, this is for binary classification. And the multinomial classification is also possible, but the support vector machine isn't good at the classification for more than 2 groups. Some people make theories, but I think it's not really good. And also the regression version, support vector regression, SVR. So this is for regression. So support vector regression is not really exactly the same as support vector machine, but we use somewhat similar idea. Yeah. And yeah. So the linear regression and yeah, so the support vector machine and the support vector regression are even farther away compared to linear regression and logistic regression. So it's pretty different, but ideas are somewhat similar, support vector machine and support vector regression. Okay, so you can apply this method if you are doing the binary classification problem in the final project or regression problem in final project. But basically this chapter, the focus is on binary classification. Maybe we can discuss some of the regression version. Okay, so at first we explain the concepts. Maybe before that we discuss several things. So we have the model named the neural network. So neural network that we don't cover in this class, but this is basically the 2 layers of logistic regression. So we have the X and Y, and if Y is the binary response, then we use logistic regression. But the logistic regression basically fits the probability. So basically, if we have X, then fitted value is the logit function. And the neural network is basically logistic regression twice. Okay, and the neural network was popular in 1980s and 1990s, I believe. And after that, after 2000, the support vector machine, becomes a hot topic, and it's really popular. Then after that, actually the neural network improved, and now all people use the deep learning that is basically a neural network. So support vector machine was really popular when I was a graduate student, but now it's losing some popularities. So it requires a lot of mathematics, but the performance is not as good as deep learning. So that's today's people's concept, path. But of course, it has advantages. Neural network, okay, theoretically, maybe, not theoretically. Neural network does not have much theory. Yeah. So practically, if you optimize all hyperparameters very well, it works very well. But sometimes the solution does not converge in your computer. And sometimes you cannot optimize hyperparameters. So it's really, depends on the analyzer's skill, human skill. So it's a kind of, the contradictive that we want the machine do everything, but actually we have to optimize more hyperparameters by very skilled workers. Support vector machine is more sophisticated method. So we have just a unique solution, and it's guaranteed that we can get the solution with very short time. So it has pros and cons against neural network. And at first, we start with some concepts. Oh, before that, how many people have heard of support vector machines?
I have.
I've heard of them, but
have.
I've never used them.
Have you used it?
I have in Python.
Okay.
No,
For
not
some
really.
time. Not really. I see. Yeah. Okay, that's great. Okay, so we start with the idea. So at first, we define several the basic things. What is a hyperplane? If you're a math major, maybe you have already known that. So in a p-dimensional space, I mean just R to the p. Okay, so p-dimensional space, a flat affine subspace of dimension p-1 is the hyperplane. So in short, is if the one-dimensional case, any point is a hyperplane. So basically, the hyperplane separates the original set into two parts. Okay. So point is a hyperplane. If p is equal to 2, that is a plane, the hyperplane is like this. Okay, so this is
Sorry,
hyperplane.
Professor, we don't have your
Yep.
screen, the slides.
Oh, sorry. I think that I have to push yes. Yeah, sorry. Yeah, sorry. Okay, so what is a hyperplane? Hyperplane. In a p-dimensional space, the RP, a flat affine subspace of dimension p-1 is a hyperplane. If p is equal to 1, the any point is a hyperplane. So hyperplane separates the original space into two pieces. So you can see that this is the one piece and this is another piece. And if p is equal to 2, any straight line is a hyperplane. So if we have the two-dimensional space, the plane, then we have the straight line. So any straight line separates this into two pieces. P is equal to 3. In a three-dimensional space, any flat plane is a hyperplane. So hyperplane, there should be flat, and the dimension is 1 lower than the original space. P is equal to 4, any three-dimensional flat space is a hyperplane. Okay, so that is, for example, in R4, that we can describe any point as the x1, x2, x3, x4. Then, for example, the 2 times x1 plus 3 times x2 plus the 4 times x3 plus 5 times x4 is equal to 10. So this is an example of hyperplane in R4. So mathematically, this equation defines hyperplane in RP. So this is hyperplane. And now that we are thinking about the classification problem, so that we have the observations x1 to xn, that each of these is in RP. And suppose each point has a label. So basically we have the pair of x1, y1 and x and yn and so on. And the y sub I is either -1 or +1. So just for technical reason, we use +1 and -1 rather than 0 and 1. Then if these observations are separated perfectly by hyperplane, then we can say one side of the plane, the yi is equal to 1, and on the other side of the plane, hyperplane, the yi is -1. So perfectly separates means these cases. So suppose that this group, one group, okay, so this is the label -1 and this is label 1. Then you can see that the blue dots and these purple dots are separated perfectly by this straight line. So you can see so this line that perfectly separates these two groups. But actually, you can see, as you can see in the left pane, that we have infinitely many straight line which can perfectly separate the two groups. So because of this reason, if the two groups are separable, the logistic regression does not work well. So basically, this normal vector, so this direction is the logistic regression's the parameter. Okay, so if logistic regression, the probability of y is equal to 1 is the logit function of beta naught plus beta 1 x1 plus beta 2 x2. Basically, this normal vector to the separating hyperplane is the beta 1, beta 2. So if we have infinitely many the separating hyperplane, actually this vector is not stable. So that means the beta 1 and the beta 2 have a high standard error. Yeah, but basically we want to formulate in this way. Hyperplane. So we wanna find the best hyperplane to separate two groups. And now that we are thinking about just simple case that the two groups are perfectly separated by hyperplane. But if we have infinitely many hyperplane, obviously we have estimation problem. So we would like to add one more condition to make that hyperplane unique. So then the idea is the maximal margin classifier. So basically that we want to maximize this distance between the observations and this separating hyperplane. So actually these are the same. So distance, yeah, I would say maybe d. So this distance, so at least these observations have the distance of d from the separating hyperplane, and we maximize this d, or actually the capital M we use, since we want to maximize it. So in this way, we can uniquely determine this separating hyperplane. So the solution is unique. That is from benefit, but also this idea works good to minimize the test error. So suppose that we have much more observations. Then where are the blue dots? Possibly, maybe some of them, maybe many of them are around here, but some of them may be around here. Right? So if the separating hyperplane is in a different location, such as maybe here, still, it perfectly separates the training set. But for test set, some observations are actually not classified perfectly. The same thing for these purple dots. If we have the larger test set, probably the most of them are around here, and we don't have any problem. But some of them comes here, possibly comes even here. But in that case, anyway, we cannot avoid error. But so these observations are separated correctly if we use the maximal margin classifier. So the maximum margin classifier separates two groups perfectly, and also it maximizes the distance, capital M, smallest distance between the boundary and the observation. And of course, this is the perfect separation is a condition. So all red points should be this side, purple points should be this side, and all blue points should be this side. So in usual cases in two-dimensional predictor space, basically we have the 3 points determine this maximum margin classifier. So basically this point and this point, and this point basically defines the maximum margin classifier. Yeah, sometimes we say optimal, the separating hyperplane. And since these 3 points defines the maximal margin classifiers, these are called the support vectors. Basically, these 3 points, the supports the the boundary, the maximum margin classifier. And of course, sometimes we have more than 3 points. And actually, if the dimension is higher, we have more support vectors. And also, even the dimension is not high, still we can have more support vectors in some cases. Yeah. So that's why the support vector machine uses this idea. So that's why we say the support vector machine. And mathematically speaking, basically this is the maximization problem because we want to maximize this distance between the boundary and the point. So maximize minimum distance between the classifier and observation. So basically we want to maximize M, the subject to this. So this is just the normalization, so standardization condition. So basically the beta 1 to beta p is normal vector which is vertical to the hyperplane. So normal vector has the length 1, then we have many good properties. And actually, if we don't normalize it, standardize it, actually it's hard to formulate it. So just we make it this, and this can be always satisfied, right? If we multiply some k, then any vector can become the unit vector. Then another condition is this. So basically, this is the quantity that appeared in the hyperplane. So this quantity times the yi, that is the larger than m. And this is the signed distance between the separating hyperplane and the observation xi. So you can see if yi is 1, then this is positive, and yi is negative 1, then this is negative. So product is always positive. So the m is positive number. So the hyperplane is as defined in the earlier slide. So I think that we have some problem. So this one. Sorry, the LaTeX does not work well. Yep. So yeah, you can see that the okay, so suppose that we have the example of two-dimensional predictor space x1, x2. Then this is the beta naught plus beta 1, x1 plus beta 2, x2 is equal to 0. Then the beta naught plus beta 1, x1 plus beta 2, x2 is the so this is x1, x2. Then this is the perpendicular. Then so this distance, the signed distance, is the beta naught plus beta 1 plus beta 1 x1 plus beta 2 x2. Yeah. Yeah, so beta naught is equal to 0. That's true. Then otherwise, that's fine. Beta naught. Yeah, so if beta naught is not here, then it's clear that the beta 1 x1 plus beta 2 x2 is the inner product. So inner product is the the signed distance of projected length. And the beta, if we have the beta 0, then we have a little more complicated case, but basically this is the signed distance. You can prove that this is the signed distance. So you can see the yeah. So maximizing m, sorry, in this maximization problem, the m is basically the minimum distance between observations and this hyperplane. So if the one group is like this, and the another group is like this, then you can see that we have margin here. Then the m is this distance. Also here m. So the support vector machine is basically the maximization problem that described in this by these two equations, two conditions. So we have to optimize beta naught, beta 1 up to beta p, and to maximize m. Yeah, but okay, so this maximization problem does not sound easy, but still we have unique solution. So we don't have a problem common to the neural network. So neural network, basically, parameter is not identifiable. We have the many parameters, many possible solutions. We don't look for, so in a neural network, basically, we don't look for the unique solution. Just we increase the likelihood, and when likelihood does not improve, then we stop. That is the algorithm. But the support vector machine, the more secure the method, so that it's guaranteed that we have the one set of parameters which maximize m. Yeah. So yeah, so the basic idea of the maximal margin classifiers is this, but practically most problems are linearly non-separable. So the example is this. So you can see the blue dots and the purple dots, and for any line, we cannot perfectly separate two groups. For example, if we make maybe this line, then we have maybe this line isn't good, so maybe want blue, so maybe like this. Okay, then okay, so this is misclassified, this is misclassified, this is misclassified. So we have the three misclassification, and for any straight line, we cannot get perfect fit. And in this case, we allow some errors, a few errors. So, okay, so except for these three, actually m is pretty small also. Okay, so maybe these are support vectors. Maybe these three are support vectors. Okay, then distance is m. So basically we have margin here. Okay, so this red straight line is the separating hyperplane, and the black band that defines m. Then we have the three exceptions. So at first, these blue points should be this side. So we have some distance from here, so we have some penalty. So suppose this is epsilon1, and also this observation should be within this range, but we have so this observation that violates that rule. So suppose this is epsilon2, and this is probably the biggest violation. So suppose this is epsilon3, then we have these three quantities as the penalty. Okay, so we penalize it later, but still that we allow a few observations beyond the black bands. So with this idea that we can deal with non-separable case. So it's a little bit contradictory. So we have the maximal margin classifier. So that means that at least the all observations are the distance m away from the border. But actually there's a few observations violates that rule. So yeah, even some observations are above the classifier. They go beyond the classifier. So that we combine two ideas. So maximal margin classifier, but there are few exceptions. So that is the idea of support vector machine. Questions so far? So far just I explained how to separate the plane into two pieces. So still it's not clear that why this works well, but I will go on. So in short, the support vector classifier, also known as the soft margin classifier, is the robust against randomness of observations. So the maximal margin rule that makes the test performance better. So as we discussed, that if we have more observations in the test set, then maximum margin classifier that works better than other boundary. And also, as a few observations are allowed to go beyond the dashed line, the hyperplane is not too sensitive to a few observations. So you can see if this rule does not apply, then boundary changes a lot. I think for example, these maybe points. So this is one group, and this is maybe another group. Then what is the best boundary? Best boundary is probably this. Okay? And this distance is m, distance is m, distance is m. And these three observations are support vectors. But if we have just one additional observations, the situation is much different. For example, what? Maybe suppose we have just one additional observation here. Then probably the separating hyperplane is here. Maybe m here, and m here, m here. So even separable cases, if we add just one observation, then the straight line totally changes. But if we allow the few observations go beyond the straight line, then beyond maybe the dashed line, beyond the dashed line, the boundary does not change much. So that is the one benefit of having this rule. So the larger m is better. Larger m is better. So if we have additional observation here, just we keep this straight the boundary, and just we pay some penalty for this violation of epsilon 1. So that we just balance between the penalty and the size of m. Then the result is much more stable. Yeah, actually, I have another page, but I just wanted to write down this graph. So mathematically speaking, basically we add another condition. So originally we have the problem of maximizing m subject to the sum of beta j square is equal to 1, and this is larger than m. But here, we have additional condition that we allow up to the error of total error of c. And the m minus 1 minus epsilon. Yeah. So yeah, so originally m, right? So m is m times 1. But we allow the error of negative m epsilon 1, basically. So yeah. So as long as the error size is up to c, actually it's divided by so the total error size epsilon I times m. So maybe I would say that this distance isn't m, but this distance is this is not the epsilon 1, but this is the m times epsilon 1. So this is the correct description. Maybe here also the m times epsilon 1, m times epsilon 3. So just we multiply this kind of constant. But as long as the total error size epsilon I is less than or equal to c, basically we allow those observations. So under this condition, we want to maximize m. So that is the mathematical formulation of the support vector classifier. So maximal margin classifier with a few exceptions. So this means many observations can violate actually if the error size is small, but the total error size is bounded by c. And here the c is a tuning parameter, so a kind of hyperparameter. So we have to optimize it maybe by cross validation. Yeah, so like this. So yeah, so the first case that we have the two groups, and actually this is separable. This is separable, but just the difference is that we have m here. Okay, but if we set this m, actually the observation number 8 and observation number 1 that violates the rule. So all blue observations are within this range, right? Within this range, but the observation 8 isn't in this range. And also the purple observations that should be within this range, but this violates that situation. So we have to pay penalty. So penalty, the size of penalty is that this is the m times epsilon 1, right? And this is m times epsilon 8. And all other epsilons are 0. So epsilon 2, epsilon 3, epsilon 4, epsilon 5, 6. So these are 0. Just the epsilon 8 and epsilon 1 is non-zero.
We don't have any condition that epsilon should be less than 1.
No, actually the epsilon can be more than 1, but in this case, actually epsilon is less than 1. That's true. So this case, okay, so this case epsilon 1 is less than 1 and epsilon 8 is less than 1. But this case, it's not really. So you can see that all purple observations should be here, but the one observation then here and here we have errors, and you can see that this distance is m times epsilon 1. This size is m times epsilon 11, but this distance is m, so that means epsilon 1 is less than 1, but the epsilon 11 is more than 1. So epsilon more than 1 is allowed. So just the total error size matters. Total error size should be within some number, but this. So yeah, so this happens because the C is large. C is large. So in this case, we have two errors, and probably C is around 1. C is maybe, I don't know, C is 1.1 or something. So the all epsilon is within the boundary at least, but yeah, but still these are small. But here, the probably C is larger. The C is, we have actually the 4 observation violates the rules, and probably C is around maybe 4 or something. So the epsilon 1 is 0.5, but the epsilon 1 maybe 1.3. And also the observation here, it violates, so that this is m times epsilon 8. Epsilon 8 maybe 0.5, and epsilon 12 maybe even 2. Actually, we can even go further away. Epsilon 12 is around 2, but sometimes maybe 11th observation, 12th observation is here. So the epsilon 12 maybe 2.5. Just the total error is bounded. So epsilon 1 plus epsilon 8 is 1. Here epsilon 1 plus epsilon 8 plus epsilon 11 plus epsilon 12 is equal to 4. So in this case, the still classifier at it is linearly separable. But if we apply support vector classifier, these observations violates the rule. And here, it even violates more. And here's another example for different Cs. So this is the small not sure. This is, I think, the small c, and this is large c. Yeah. Maybe not. Large m. So this estimated m is large. That is for sure, right? So the m is this distance. So m is large, and this is m is small. So we want to maximize m. So m is large. Actually, sorry, this is probably large c. Large c is basically we have the weaker condition. The large c, they are more flexible to determine boundary. So that's why we can get a larger m. And most observation violates the rule. Actually, all observation violates the rule probably. So this observation and this observation maybe barely satisfy the condition, but other observations, all other observations violates the rule. And here, only few observation violates the rule. Maybe only observation violates the rules are maybe these 6 observations, but instead of that, m becomes smaller. Yeah, large C, basically the simpler boundary. It's not clear here, but yeah, but anyway, so we are still talking about hyperplane. So yes. So in this way, the support vector classifier works. So based on this idea, the next time that we discussed how support vector machine is made. So support vector machine basically consider a so-called feature space. It's a higher dimensional space. Then that we can separate the very complicated problem. I mean, we make the complicated problem into linearly separable case. Okay, so I stop here, and the next time that we discuss the rest of the actually 9.3, and that we discussed the coding for support vector machine. That we don't cover 9.4 and 9.5. Okay, so sorry, it's already 8:20, so see you on Wednesday.